Hello everyone, this is Swati from Aeronautical Engineering. Today we are here for the seminar topic of aerospace propulsion called micropropulsion for CubeSats. So let's begin with the topic, micropropulsion for CubeSats. Understanding hypersonic flow. The study of hypersonic lifting body dives into vehicle traveling at speed greater than Mach 5, where the air behaves very differently that at typical aircraft speed. Imagine a space plane re-entering Earth's atmosphere. This compresses the heat up instantly around it. The extreme environment introduces complex fluid dynamics such as intense shock waves and high temperature gas effects. Analyzing the performances is crucial for designing future space vehicles and high-speed atmospheric flights, ensuring they can glide efficiently and survive the harsh terminal and aerodynamic loads. We're essentially trying to predict how these high-speed gliders will behave in a super fast, super hot world. The nature of lifting bodies. Lifting bodies are unique class of aerospace vehicle designed to generate significant lift using the shape of the fuselage rather than relying slowly on traditional wings. Think of the early space shuttle prototypes of modern commercial space vehicles that have a rounded blunt shape. This design is partially beneficial at hypersonic speeds because it helps manage the extreme heat generated during high-speed flight by having blended body wing design. They can achieve better lift to drag ratio at high Mach number, allowing the greater maneuverability and a wider landing footprint upon re-entry. Introducing perturbation equations. A tackle complexity of hypersonic flow mathematically. Engineers often turn to perturbation equation, the simplified form of the complete nonlinear governing fluid dynamics equation, the Navier-Stokes equation that work by assuming the flow deviates only slightly for perturbation from a known simpler baseline state. The technique is a powerful way to reduce the overwhelming computational burden associated with solving the full equation. It breaks the massive problem down into manageable linear spaces, making it feasible to analyze complex structure like subtle changes in surface pressure and heat flux. The role of numerical solutions. Since the quantification equations, even in the simplified form, are still complex differential equation, we often cannot find a neat algebraic answer. This is where numerical solutions comes in. Thus, innovations using computational methods like finite differences of finite volume schemes to approximate the solution across a grid point surrounding the lift body instead of one perfect formula. We can highly detailed map of flow properties like pressure, velocity, and temperature at thousand locations. This allows of precise point-to-point performances analysis providing the granular data needed to for accurate vehicle design. Governing flow equations. The foundations of this analysis is set on the governing equation of fluid motion, namely the conservation of mass, momentum, and energy. At hypersonic speed, these equations are nonlinear, meaning small changes in one variable can lead to disappropriately large change in others. The perturbation methods cleverly linearize these equations often around a simple uniform flow conditions to make them solvable. Understanding this fundamental physics principles is the essential first step before an computational method can be applied to predict a lifting body aerodynamic forces and heat transfer characteristics. Simplifying assumptions in analysis. To make a problem computational tractable, several simplifying assumptions are frequently made. For instance, inviscid flow assumption, where the effect of viscosity frictions are ignored in the bulk of the flow field, is common through a boundary layer. analysis must be used near the surface. We might also assume the flow is two-dimensional or asymmetric initial before moving into a 3D analysis. These steps are not shortcuts but strategic reduction and associate the most dominant physical effect along and faced step by step increasing in model complexity until the desired level of accuracy is achieved. Boundary layer analysis. Crucially important at hypersonic speed is the boundary layer with the thin region of viscous flow right next to the lifting body surface. Even with simplified perturbation equation for the outer flow, the boundary layer must be treated separately because it decays the critical factors of skin friction, drag, and aerodynamic heating. This intense heat generated here can melt conventional materials. Therefore, the numerical solutions must carefully couple the other inviscid flow solution with a separate viscous boundary layer solution to accurately predict the thermal production system requirement and total drag. The method of characteristics. One classical technique often used to understand the uh, structure of the flow field, especially for the inviscid flow part, is the method of characteristic MOC. While often, so, while often by the model compression fluid dynamics, it provides deep physical insight into how disturbances propagate through the supersonic and hypersonic flow. Applying MOC to the linearized perturbation equation can help map out the shock and expansion waves that dictates the pressure distribution over a lifting body, giving intuitive senses for the aerodynamic forces before engaging in heavy numerical solutions. Hypersonic similarity parameters. A useful concept for scaling and relating different hypersonic flow conditions is the hypersonic similarity parameters. This dimensional inverse helps consolidate the effect of Mach number and body shape into a single variable, which is particularly useful when applying perturbation methods. It allows engineers to take results from test or simulation of the one shape at the mat one shape at the Mach number and apply them to slightly different shape or space. This is essential for design optimization, saving immense amount of time and computational power by leveraging existing data with a perturbation analysis. Calculating lift and drag. The ultimate goal of the analysis is to accurately calculate the lift and drag forces acting on a lifting body. This achieved by integrating the numerical determined pressures and shear stress distribution over an entire surface area of the vehicle. The perturbation equation provides the pressure field and the boundary layer solution provides the shear field. The ratio of these two forces, lift and drag ratio, is the key metric of aerodynamic efficiency. A higher means a vehicle can glide further and have better energy management during atmospheric flight and re-entry. Thermal protection system modeling. A critical output of an analysis is the prediction of aerodynamic heating, which directly informs the design and the thermal protection system. The numerical solution of the perturbation equation and the boundary layer is at a high flux that rate of high heat transfer of the surface. The data decays the material and needed like Albert's shield and ceramic tags and their necessary techniques to prevent the structure from overheating. This is a life to the design parameter and resources from the numerical perturbation solution is paramount to ensure mission success and crew safety. Numerical stability and accuracy. When running a numerical simulation of the perturbation equation, engineers must carefully consider numerical stability and accuracy. An unstable scheme can provide non-physical oscillations or errors that grow over time, making the result meaningless. Therefore, appropriate numerical techniques like implicit schemes or careful selections of the time step must be employed. Furthermore, grid convergence studies are performed where the grid resolution is increased to ensure the solution no longer changes, confirming the accuracy of the final numerical result. Validation of with experimental data. No simulation is completely complete without validation, and the numerical results from the perturbation analysis are recognized compared against experimental data obtained from the internal test or actual flight test. High enthalpy hypersonic wind tunnels can partially replicate the conditions, providing critical pressure and the heat flux measurements when the numerical solution closely matches and experimental measurements confidence in the model is established. This initiative process of simulation testing and refinement is fundamental to the successful development of an hypersonic vehicle. Computational fluid dynamics CFD. When the perturbation methods offer computational shapes and fast way to gain the initial design inside the full non-linear computational fluid dynamics simulation, serve as the final high fidelity check. The perturbation solution is often used to check, explore a wide design space, and the most promising design is the subjected to the much more expensive full CFD simulation. That agreement between a simplified perturbation analysis and the full CFD result is powerful indicators of the robust and validity of the initial faster design iteration, future application and design mission. By the seeing the first figure, we can analyze how the MATLAB code is working on the propellant mass of CubeSat micropropulsion. This insight gained from the numerical solution, the perturbation equation are immediately feedback into the design into an initiated process. For example, that the analysis predicted excessive drag, the body shape can be subtly modified, perhaps by changing the leading edge shape or the bloodless of the noise, and the analysis can be quickly rerun. This rapid prototyping loop is essential in modeling aerospace engineering as a computational power. Thank you.